Hello everyone and welcome back. In the previous lecture I have posted one problem based on cut vertices and cut edges. So let us first go through the solution to that problem. A graph was given to you and you were asked to list down all the cut vertices and cut edges. So let us check for each vertex and list down who are the cut vertices in this graph. So we start with the vertex A. Here we can see the vertex A is a pendant vertex and we know a pendant vertex is never a cut vertex. So A is not a cut vertex. Next we move to the vertex B. If we delete the vertex B from the graph, this is the graph that we obtain. The number of components increase because the original graph G had one component. After the removal of the vertex B, the graph is having two components. So removal of B from the graph is increasing the number of components in the graph. That is the reason B is a cut vertex. So I list down the vertex B under cut vertices. Similarly, next if we see for the vertex C, when C is deleted, the number of components increase and therefore C is cut vertex. D is pendant vertex again, which is definitely not a cut vertex, and that you can check also. If you delete D, the number of components will not increase. Next we come to the vertex E. If E is deleted, number of components are not increasing, so E is not a cut vertex. Next if we delete the vertex F, the number of components increase and therefore F is cut vertex. Removal of G increases the number of components, so G is a cut vertex. Removal of H does not increase the number of components, so H is not a cut vertex. I again is a pendant vertex and hence is not a cut vertex. So in this graph G, only B, C, F and G, these four are cut vertices. Next we come to the edges. As discussed in the previous lecture, we know that if an edge in a graph is part of some cycle, then it is not a cut edge. If it is not part of any cycle, then it is cut edge. So using that property, we will decide whether an edge of this graph is cut edge or not. So let us start with the edge AB. As we can see here, AB is not part of any cycle in the graph, so AB is cut edge. That you can check also yourself. By deleting the edge AB, you will see the number of components increase. Hence AB is cut edge. Similarly, BC not being part of any cycle is cut edge. CD is not a part of cycle, so CD is cut edge. CF is also cut edge because it is not a part of any cycle. Now when you come to the edge EF, EF is part of the cycle EFHE, and therefore being a part of the cycle, the edge EF is not a cut edge. And for similar reason, the edge EH and FH, these two edges also being part of cycle are not cut edges. Next, the edge FG is not a part of any cycle and therefore is a cut edge. Same is for the edge GI, which is also not part of any cycle, therefore it is also a cut edge. In the next question again, we were asked to list down all the cut vertices and cut edges for the Peterson graph. So this is how the Peterson graph looks like as is drawn here. Let us check for the vertices who are cut vertices and which are not. We start with the vertex A. The original graph G has one component, so if we delete the vertex A from this graph, the number of components still remains 1. So removal of A is not increasing the number of components in the graph and therefore A is not a cut vertex. Similarly, you can check for the vertex B. Its removal also will not increase the number of components, therefore B is also not a cut vertex. Similarly, C, D, E, none of these vertices are cut vertices. Next we check for the vertex F. So if I delete the vertex F, still my graph remains connected, number of component is still 1, there is no increment, so F is not a cut vertex. In a similar manner, if you check for all the remaining vertices, you will find that removal of any vertex in the graph is not going to increase the number of components. So none of the vertices in this graph is cut vertex. So Peterson graph has no cut vertices. Cut vertices, none. Next we come to cut edges. Here if you observe carefully, you will find that every edge in this graph is part of some cycle. For example, if I consider the edge AB, AB is part of the cycle A, B, C, D, E, A. Okay. Similarly, if you consider the edge GJ, GJ is part of the cycle G, J, H, F, I, G. So every edge is part of some cycle in the graph and that is the reason none of the edges in the graph is cut edge. Therefore, Peterson graph has no cut edges also. So you can remember Peterson graph as a graph which has no cut vertices and no cut edges. Now in today's lecture, we are going to discuss elaborately about adjacency matrix and incidence matrix of a graph. So we start with the adjacency matrix. Here goes the definition. Let's go through the definition first and then I'll explain with the help of some examples. So suppose you are having a graph G of order n. There are n vertices which are named as V1, V2, V3 up to Vn. Then the adjacency matrix of the graph, which is denoted by AG, is the n cross n square matrix, So as many vertices you have in the graph, whatever is the order of the graph, that is basically the order of your matrix, and it is a square matrix. So if you have 5 vertices in the graph, then your adjacency matrix is going to be a 5 cross 5 square matrix. Okay. And how is the matrix created? The entries Aij is basically calculated by the number of edges of the graph which are having the endpoints Vi and Vj. And just to confirm, you can check adjacency matrix is always a symmetric matrix, so that the entry Aij is always equal to the entry Abi. So let's see with the help of examples so that it becomes more clear. Here I have taken a very simple example of P2. I will draw the adjacency matrix of this graph. So the adjacency matrix will be denoted by A of the graph, AG1. Okay. Now as we can see that this graph G1 has order 2, since there are 2 vertices. So the adjacency matrix is also going to be a 2 cross 2 square matrix. For your convenience and simplicity, you can just mention the name of the vertices as labels of your rows and columns, because the order of the graph is basically the number of rows and the number of columns in your adjacency matrix. So the vertices that you have A and B, you can just label your rows as AB and your columns as AB. So it will be more easier to put the entries within the matrix. Okay, let's see how we can fill up this matrix entries. So the very first entry of the first row, first column of the matrix is corresponding to the vertices A and A. That means this entry is going to be the number of edges present in the graph having endpoints A and A. But in the graph we do not have any loop at the vertex A, so there is no edge having A as both the endpoints. So the entry here is 0. Next, for the first row, second column, I am corresponding to the vertices A and B. That means how many edges are there in the graph with A and B as endpoints. As we can see in the graph, there is only one edge, that is AB, having the endpoints A and B. So the entry here would be 1. Next, for the second row, first column, it is corresponding to the vertices B and A. And number of edges in the graph having B and A as endpoints is only 1. There is only one edge, that is AB itself. And for the last entry of the matrix, second row, second column, I can see it is corresponding to the vertices B and B. So in the graph, I can see there is no edge with B as both the endpoints, that is there is no loop at the vertex B. So this entry is going to be 0. Okay. Again, you can observe clearly that the adjacency matrix is a symmetric matrix. So that is one property that can also help you to fill up different entries of the matrix. Let's move to the next example. Here I am having a P4 basically. So the adjacency matrix can be constructed as a 4 cross 4 matrix because the order of the given graph G2 is 4. See, I have also labeled the rows and the columns with the names of the vertices itself as A, B, C, D. Now let us fill up the entries of the matrix. So the first row, first column corresponds to the vertices A and A. As in the graph, there is no loop at the vertex A, so this entry is 0. Then for this entry, I need the number of edges between the vertices A and B. There is only one edge between the vertices A and B, so this entry is 1. There is no edge between the vertices A and C, so this entry is 0. And similarly, there is no edge between A and D, so this entry is also 0. Okay. Now see how I use the symmetric property of the matrix to fill up some entries of the matrix itself. As I know it's going to be a symmetric matrix, so the first row entries are going to be my first column entries as well. So 0, 1, 0, 0, this is the first row. I will have the same as my first column 0, 1, 0, 0. So I can just fill up my first column 0, 1, 0, 0. This is symmetric property. So for this entry I need how many edges are there with B as both the endpoints. No loop at the vertex B, so this entry is 0. Between B and C there is one edge. Between B and D there is no edge. Again see the second row is 1, 0, 1, 0 and that will be the same as my second column. So it is 1, 0, 1, 0. So here I can just put 1, 0. This is how I use the symmetric property to fill up some of the entries. Next for this, between C and C no loop, so it is 0. Between C and D there is one edge. Again third row is 0, 1, 0, 1. So the third column will be 0, 1, 0, 1. And lastly between D and D there is no edge, so it is 0. This is the adjacency matrix for the given graph G2. Now let us quickly draw the adjacency matrices of the different graphs in the subsequent examples. So here at the vertex A there is no loop, between A and B one edge, between A and C there is one edge, between A and D there is no edge. I immediately fill my first column as soon as I get my first row 0, 1, 1, 0. Between B and B, no edge. Between B and C, there are two edges. See, between the two vertices B and C, you can find there are two edges. So, this entry is 2. Between B and D, there is no edge. Immediately, I fill up my second column, 1, 0, 2, 0. Between C and C, no edge. Between C and D, 1 edge. Immediately, I fill up my third column as soon as I get my third row, 1, 2, 0, 1, 1, 2, 0, 1. Between D and D, no edge. This is the adjacency matrix, which is 4 cross 4 square matrix because my order of the graph is 4. Here the order of the graph G4 is 6. So, my adjacency matrix is going to be a 6 cross 6 matrix. I have labeled the rows and columns by the name of the vertices. So, let us start to fill the matrix. There is no edge having U as both the endpoints. So, the first entry is 0. Between U and V, there is one edge. Between U and W, there is no edge. Between U and X, no edge. Between U and Y, one edge. Between U and Z, no edge. First row done. So, immediately fill the first column 0, 1, 0, 0, 1, 0. Between V and V, no edge. Between V and W, one edge. V and X, one edge. V and Y, 0, VZ, 0. So, I have 1, 0, 1, 1, 0, 0. Next, between W, W. Now, you can see in the graph, there is a self loop at the vertex W. So, there is an edge which starts at W, again ends at the vertex W itself. Now, whenever such a case arises, whenever you have a loop at any vertex, in the adjacency matrix, the entry corresponding to that loop is taken as 2. So, basically an entry 2 is considered for each self loop that is present at a vertex. So, if you have more than one self loop at a vertex, more than one loop at a vertex, then as many loops you have, for each loop you add an entry 2. Between W and X, there is one edge. Between W and Y, 0. W and Z, 0. So, the third row is 0, 1, 2, 1, 0, 0. So, the third column will be 0, 1, 2, 1, 0, 0. Between X and X, no edge. Between X and Y, 1, X, Z, 0. So, I have fourth column as well. Between Y and Y, no edge. Between Y and Z, one edge. So, here I have 1. Between Z and Z, no self loop at Z. So, it is 0. Here the graph G5 has 5 vertices. So, the adjacency matrix is 5 cross 5 square matrix. Between A and A, no self loop at A. So, it is 0. Between A and B, one edge. A and C, one edge. Between A and D, 0. And between A and E, 0 edge. Immediately, I fill the first column. B and B, no edge. B and C, there is one edge. Between B and D, one edge. Between B and E, 0 edge. So, 1, 0, 1, 1, 0. C and C, no edge. C and D, no edge. C and E, no edge. So, I have zeros here. Also, between D and D, 0 edge. Between D and E, no edge. So, this is also 0, and between E and E, there is no edge. Now, after you have constructed your adjacency matrix, there are some properties that you can check to confirm if your adjacency matrix is drawn correctly. First of all, the matrix will be a square matrix definitely. Secondly, it will be a symmetric matrix. So, that is one property that you can check. And lastly, you will see that since each row or each column is corresponding to some vertex. For example, the first row is corresponding to the vertex A, or the third column is corresponding to the vertex C. So, every row or column is corresponding to some vertex. If you sum up the entries of any row, you will find it to be the degree of the corresponding vertex. Similarly, if you sum up the entries of any column, you will find it is the degree of that corresponding vertex. Let me clear it out. For example, this is my row corresponding to the vertex A. If I sum up the entries of this row, that is 0 plus 1 plus 1 plus 0 plus 0, the total sum is 2. You see in the graph the degree of the vertex A is 2. A has degree 2, right? Similarly, if you see the fourth row, it is corresponding to the vertex D. The sum of all the entries in the fourth row will give you 1. And if you see in the graph, the vertex D is a pendant vertex of degree 1. If you see the third column, that is C, if you sum up all the entries of the third column, you will find the total sum is 2. In the graph, the vertex C is having degree 2. You can sum up the entries of the fifth column, that is corresponding to vertex E. The total sum of the entries of column 5 is 0. And the reason is the degree of the vertex E is 0. It is isolated vertex. So, you can sum up the entries of each row and check whether that matches with the degree of the corresponding vertex, or you can sum up the entries of each column and check whether it matches the degree of the corresponding vertex. So this is one important property that you can check and confirm if your adjacency matrix is drawn correctly. Now we come to the next concept, that is of incidence matrix of a graph. Here goes the definition. The incidence matrix of a graph G, which is having n vertices named as v1, v2, vn and m edges named as e1, e2, em, will have an incidence matrix which is denoted by mg. It is n cross m matrix. So basically the order of the graph will be the same as the number of rows in the incidence matrix, and the size of the graph will be the same as the number of columns in the incidence matrix. So it is not always a square matrix unless the number of vertices and the number of edges in the graph are same. So in which the entry mij of this matrix is taken as 1 if vi is an endpoint of the edge ej, otherwise it is taken as 0. What happens for the loops, that I will discuss when I will go through the examples. And just remember, if you are dealing with loopless graphs, no loops, then incidence matrix is 0, 1 matrix. 0, 1 matrix means a matrix in which every entry is either 0 or 1 and nothing else. That is 0, 1 matrix. Let's see with the help of example to clear this concept. Again, I am dealing with the P2 first. Now remember, in case of adjacency matrix, since the matrix order depends upon only the order of the graph, that is the number of vertices, so only labeling the vertices was fine. But while you are dealing with incidence matrix, since the order of the incidence matrix depends upon the order as well as on the size of the graph, so you need to label the vertices as well as the edges of the graph. So here I have labeled the only edge present in the graph as E1. So the incidence matrix denoted by mg1 will be, since the order of the graph G1 is 2 and the size of the graph G1 is 1, so my matrix mg1 is going to be a 2 cross 1 matrix. Number of vertices in the graph is same as the number of rows and the number of edges in the graph is the same as the number of columns. So I have labeled the rows and columns accordingly. Now what about the entries? What you will do is just go column by column. Here you only have one column. So come to that column, focus on it. You are dealing with the edge E1 here. Go to the graph, see that which are the end vertices of this particular edge E1. You can see E1 is having the end vertices u and v. Then among the rows of the matrix, you search for those rows corresponding to the end vertices of E1, that is u and v. Here I have only those two rows, and for each of those two rows corresponding to the two vertices, I will just put a 1. So basically the idea is, you come to a column in the incidence matrix that will correspond to an edge. Go to the graph and see that particular edge is having which two vertices as end vertices. Corresponding to those end vertices, the rows that you have in your incidence matrix, just put a 1 for those particular rows and all the remaining would be 0. Let's go through some other examples to clear it out. Here I am dealing with a graph G2 which has 4 vertices and 3 edges. So I am going to get my incidence matrix as a 4 cross 3 matrix where I have labeled my rows, 4 rows with 4 vertices, and I have labeled my 3 columns with the names of the 3 edges. Now see how to fill up the entries. I will go column by column. So I come to the first column, E1. This column is corresponding to the edge E1. In the graph I can see the edge E1 is having u and v as the endpoints. So under the column E1, find out the rows corresponding to the vertices u and v. This is the row corresponding to u, this is the row corresponding to v, and those entries are going to be 1. So only those vertices which are end vertices of the corresponding edge that we are talking about, they are 1 and the remaining will get a 0. Then I move to the next column that is corresponding to the edge E2. In the graph, the edge E2 is having v and w as endpoints. So corresponding to the row v, there will be a 1, corresponding to the row w, there will be a 1, and remaining would be 0. Lastly, we come to the column E3. In the graph, E3 is having x and w as end vertices. So corresponding to x and w, we will have a 1 each and the remaining would be 0. So this is how we create the incidence matrix of a graph. Let's see some more examples. Here the order of the graph G3 is 4 and the size of the graph G3 is 5. So my incidence matrix is a 4 cross 5 matrix. Come to the column corresponding to the edge E1. E1 is having end vertices u and v. So corresponding to u and v, we have 1 each and others are 0. Then we move to the column E2. E2 is having U and W as n vertices. So corresponding to U and W, we will have a 1 each, others are 0. Then we move to E3. E3 is having W and X as n vertices. So they will be having 1 each. For U and V, it will be a 0. Then we come to edge E4. E4 is having V and W as n vertices. So V and W, those corresponding rows will have a 1, others will have 0. Same is for E5, because E5 is also having the same pair of vertices V and W as n vertices. So V and W will have 1 and the remaining will have 0. Now just like adjacency matrix, there are some properties that you can check to confirm whether your incidence matrix is constructed perfectly or not. Here you can see every row is corresponding to a vertex in the graph and every column is corresponding to an edge in the graph. For example, here the first row, it is corresponding to the vertex U. If I sum up the entries of the first row, I get 1 plus 1 plus 0 plus 0 plus 0, that is a total of 2. In the graph, you will find the degree of the vertex U is 2. See, the vertex U is having degree 2. Similarly, if we check the third row, it is corresponding to the vertex W. The sum of all the entries is 4 because the vertex W is having degree 4. Now, if you check the sum of the entries of a column, what will you find? You will find that corresponding to each column, that is corresponding to each edge, the sum of the entries is always equal to 2. See, corresponding to the first column, sum is 2. Corresponding to the second column, sum is also 2. Same is for third, fourth and fifth column. That is corresponding to every column you are getting a total sum of 2 only. The reason is every edge corresponds to 2 end vertices. Let's go to the next problem. Here my graph G4 is having 6 vertices and the size of the graph G4 is 8. So my incidence matrix is a 6 cross 8 matrix. Let me fill up the entries. Corresponding to the edge E1, U and V are the end vertices. So I put a 1 for U and a 1 for V and the remaining entries are 0. Next I come to the column corresponding to E2. E2 in the graph is having n vertices U and Y. Remaining are 0. The edge E3 is having Y and Z as n vertices, remaining are 0. The edge E4 is having X and Y as n vertices and the remaining are all 0. E5 is having V and X as n vertices and remaining are 0. E6 is having V and W as n vertices and the rest are all 0. E7 is having W and X as n vertices and the remaining are all 0. Lastly, the edge E8, as you can see in the graph, E8 is a loop present at the vertex W. So for the edge E8, both the endpoints are W only. That is the reason corresponding to the row for the vertex W, I put an entry 2 and the rest are 0. Because the loop is having the same vertex for both the endpoints and that is the reason you give a 2. And you know that in every column the sum of the entries is going to be 2 only. So you can see here for a loop also the sum of the entries in that column is also 2. Okay. So here also you can cross check. For example, corresponding to the row for the vertex W, the sum of all the entries gives you a 4 in total because the vertex W in the graph is having a degree 4. And you can check for every column in this incidence matrix, the sum of the entries comes out as 2 only. Okay, now for this graph G5, the order is 5 and the size of the graph G5 is 4. So my incidence matrix is a 5 cross 4 matrix. For the edge E1, U and V are end vertices, rest are not. For E2, V and W are end vertices, remaining will get entry 0. For E3, U and W are end vertices, so remaining will have zeros, and E4 is having V and X as end vertices. There will be 1 and the rest will be 0. Here you can check corresponding to the first row, the sum of entries is 2 and the vertex U is having degree 2. Corresponding to the vertex V, the sum of entries is 3, V is having degree 3. Corresponding to the last row, the sum of the degrees is 0 because Y is isolated vertex with degree 0. And corresponding to every column, you will find the sum is 2 only. Now here I am posting a problem for your practice. This is the given graph to you. You will have to find out the adjacency and incidence matrices for this graph. So that's all for today. Thank you so much for watching. I really hope that you have understood the concepts of adjacency and incidence matrices. Keep drawing several types of graphs and keep constructing the matrices on your own. The idea will be much more clear to you. Still, if you have any doubt, any confusion or any suggestion of any kind, you can just write to us in the comment section below. We are there to help you. So if you love learning with me, then please do like, share and subscribe to our channel. I am going to meet you again soon with the next lecture of the series. Till then, thanks for watching. Take care and bye-bye.